Hey guys, welcome back. In the previous video, we just talked about the units, right? What units are. And now we're going to talk about, going back to measuring still, the metric system. The metric system is a nice system of prefixes. So it has nothing, you could have the prefixes in feet or miles or inches. You can have centi-inches. You could do it. It'd be weird. Nobody does that, but you technically could, right? Pounds. You could have kilopounds. Now, we don't use kilopounds. We use tons, but you could, all right? And so right here in the middle is the base unit, right? This is the first power, 10 to the 1, right? Or 10 to the 0, actually, all right? 10 to the 0. And that's the base unit. So this is the base unit. And that would be grams, liters, meters, etc. That's the base unit. Okay? All right. And when we talk about the metric system, we're comparing numbers, because when we measure things, we want to know, is that right? Is 5 a lot or is 5 a little? Right? Because a number without a unit, we don't have any idea. Right? Is 5 a lot? I don't know. 5 kids? Probably for some. $5? Probably not a lot. Right? 5 pencils? I don't know. You know what I mean? And so, like 5 cars, I think that's a lot, but maybe not. Maybe not for your family. Right? Maybe for a single person, maybe it is. I don't know. Right? So you need to have a unit, and we got to compare numbers. Right? When we're comparing numbers. And the metric system allows us to compare numbers that are really, really big and really, really small, right? Because what we do as humans, we live in this region right here, and we're very good between 1,000 and 0 comparing those numbers, right? 400 and 200, we get that, 400 is twice as big as 200. We're pretty good at that. Less than that, we're not so good. Like if you had a quarter-pounder hamburger or a third-pound hamburger, right? People don't necessarily know which one's bigger, right? It's less than 1. We're not good at comparing that in general, okay? Some of you are. Some of you would know, yeah, the third-pound hamburger is much bigger. But not everybody would get that, okay? And especially when we become really, really big. Like if you watch the news and they talk about spending, right? And you get, 5 billion or 4 trillion or 300 million, right? It gets confusing because we're not comparing with the same exponent. So we want to compare with the same exponent when we're talking about science. So let's go big first. All right? So when I go big, right, the first one we're going to talk about, all right, when we go big, right here is 10 to the 3rd, which is kilo. Now, you do not have to memorize this. You'll always be given the prefixes, right? But 5 km is the same thing as 5 times 10 to the 3rd meters, right? So if you run a 5K, right, where I live, it's almost 5K season, it seems like. Pretty soon there's going to be a 5K almost every weekend or every other weekend, all right? And if you wanted to run a 5K, it's a 5 kilometer, right? And that's 5,000 meters, all right? Going bigger, 10 to the 6. That would be mega, all right? I'm old enough when megabytes were big. Like you had a 512 megabit flash drive. That was huge, all right? Now, there's even bigger. We'll go 10 to the 9th, right? Which is gigabytes. And now even bigger than that, 10 to the 12th terabytes. There's even 10 to the 15th. We don't even use it. All right? So that's just big. Those are big. So, like again, 5 megabytes would be 5 times 10 to the 6 bytes, right? So 5 million bytes of information. Small. There is a D here. We don't use this one. It's 10 to minus 1, which is deci. We use centi a lot. 10 negative 2. C, all right? So if I do 15 centimeters, same thing as 15 times 10 to the negative 2 meters. There you go. And then we have 10 to the negative third, which is milli, so millimeters, all right? You know, and you talk about metric, 10 millimeter socket, all right? A very common one. And we got 10 to the minus 6. We use the Greek M, mu, micro, right? So keep going, 10 to the minus 9. Nano. So another thing we can do is you had 450 nanometers. That's the same thing as 450 times 10 to the minus 9 meters. Which leads me into scientific notation. We're going to hit that in a second. I think you guys know how to do that, though. Another one that's unique is 10 minus 10, and that's an angstrom. We're talking about atom size. You got 10 to the minus 12, which is pico, and we'll just do, what color haven't I done yet? We'll just do this one. 10 to the, which is femto. So those are the scientific notation, right, or the metric system which we use scientific notation from. So it just makes it cleaner. Like 450 times 10 to the negative 9 is not as clean as 450 nanometers. So as you know, scientific notation is just how we can compare small, right? Scientific notation, comparing large and small numbers, right? Easily. And so it's the number times 10 to the power, right? And whatever that power is, right? So it's a negative exponent, we're going to the right. Positive exponent, we're going to the left. We're getting bigger, okay? So that's the metric system. That's it. Very important, all right? So we compare things on the same scale, okay? Now, when you get answers with scientific notation, this is more important than this, all right? The number and the power is more important than the actual number. Because when you're measuring things down here or up here, is not nearly as important, right, the number as the power. For example, you win the lotto tomorrow. The power is way more important than the number up front. Because if it's 10 to the third, you won $4,000. Congratulations, but it's not necessarily a huge lifestyle change. It might make things, it's going to make things easier, right? It might give you breathing room, lots of things, but it's not like 10 to the third is totally different than 10 to the ninth. If you won 4 times 10 to the ninth dollars tomorrow, I don't think you'll be in the class the next day, right? That's a huge difference. So that exponent is a big, big deal. All right, we're just going to transition right into matter. All right, because when we're measuring, we talked about measurement, units of measure. Now we're talking about, the prefixes in those measurements. And now we need to talk about some of these things. So mass, right, is a measure of matter. We already mentioned this, right? Okay, now one thing we do in chemistry, we use the gram a lot, okay? We don't want to use kilograms in the lab. You don't want, imagine you having to buy a lab kit that you needed a pallet for, right, to put in the driveway because it has kilograms of everything. It'd be crazy, right? You don't want that. We want to use the grams and milligrams, okay? Now, because atoms are so small, sometimes we use something called the atomic mass unit. Which is abbreviated AMU. Sometimes I've seen periods between the A, the M, and the U, and sometimes I have not. All right? And so just so you know, 1 AMU is equal to 1.6605378 times 10 to the negative 24 grams. So if you look at up top of the screen here, right, that means that that's negative 15. 16, 17, 18, 19, 20, 21, 22, 23, 24. Like I'm off the page. Like that's how small an AMU is. It is tiny. It is extremely small, right? And so with that, that's why we have this unit. Temperature. Let's dive into temperature now. Your book kind of goes all over the place, and we're just trying to define things, right? So all these things, when you think about how much matter, temperature of the matter, right? All this counting, this all goes into how much. So when we talk about chemistry and reactions, we know how much of each reactant or each quote-unquote ingredient, if you go like to cooking, to use, right? Because if you've cooked anything or baked, especially baking, if you baked, you know that the amount of ingredients really matter. You can't mess with that too much, all right? That's why things like Betty Crocker and Duncan Hines, those muffins and cakes are so popular, because they have everything in the right ratio ready to go, except for a couple things like water and some other that are perishable. And so we need to know how to measure everything to do our reactions. Temperature is also important because not every reaction happens at every temperature. And some of you experience just with your electronics. Where I live, a lot of times that cell phone is too hot. And I'll tell you nowadays, that's too hot. Right? You have to put it in a cooler or refrigerator or something to cool it down. Right? Especially if you take it to the beach or whatnot. And so temperature is very important. But what is temperature? Because some of us use it for just, what am I going to wear? But right now we're going to use it for the average kinetic energy of an action, right? It's the average thermal, what we're going to call thermal energy, right? So thermal energy is a kinetic energy. It's a motion. So like we're going to learn that matter is made up of these particles, and these particles are always moving. They're not, now they might not be moving to our eye, right? But they're moving, okay? And temperature, we measure it usually because it's a thermal energy transfer, right? So temperature actually originated with Galileo way back, right? I don't know exactly the year, that's his lifetime. But the first air thermometer was in 1612. And then the first alcohol thermometer was in 1654, right? Fahrenheit invented the mercury thermometer, and Fahrenheit is kind of neat, okay? When you look at Fahrenheit, Celsius, and Kelvin, Fahrenheit, what Fahrenheit did is he took saturated solution of salt water and made that 0. And he did something with, it's close to body temperature. It's not exactly body temperature, but it's close to body temperature, was 100. And then he just divided it up. Celsius made his scale with water. When water freezes, when water boils. And then Kelvin made his absolute. Right, so Kelvin made absolute temperature. All right. So if we look at water, if you take a like water here, there is the boiling point and freezing point. So we got boiling, which we're going to learn is not a solid. It's not liquid to a gas. And melting or freezing. Which is solid to a liquid. All right. And if we look at these across the way, all right, the boiling point of water in Fahrenheit is 212. And the freezing point is 32. All right. In Celsius, it's 100 degrees Celsius and 0 degrees. Now, there is something called absolute zero. All right? And that means there's no more thermal energy. That means those particles that make up the matter that we talked about, they're not moving. Right? That's about negative 459, right? Fahrenheit. It's negative 273 Celsius. And it is 0 Kelvin. So Kelvin is 273.15 there and 373.15. All right. So as you can see, degrees Celsius to Kelvin, right? You just add 273.15. Now there is a formula for Fahrenheit to Celsius, all right? So degrees F equals 9/5 times degrees C plus 32, and you can go the other way. We'll give both of those formulas to you in the formula sheet, but you can convert them. I'm not huge on that, okay? That's not a big deal. Celsius is what we're going to do most of the time. Kelvin, we need absolute temperature. So that is a little bit more. Now, we're going to continue with density, all right? Density. Density is another property of matter. All right, and we're going to be almost done with day 2, or this video at least, with density. So density, it's a physical property. It's a density. It is a ratio of mass to volume. So it's a ratio, right? Mass to volume. The unit, the SI unit, would be kilogram per meter cubed. If you looked at what a kilogram is per cubic meter, right? A cubic meter, almost everybody that's watching this can actually fit into a cubic meter and stay alive, right? It's over 3 feet by 3 feet by 3 feet. Now it wouldn't be comfortable; you'd be bent in half, but you would survive. Most of us. There are people who cannot, but I could for sure, right? And so it's a huge amount. We are going to use, for liquids and solids, grams per milliliter or grams per centimeter cubed, right? Because 1 milliliter by definition is 1 centimeter cubed or a cubic centimeter. So if you knew that, great. If you didn't, that's fine too. Gases, we use grams per liter. All right. Okay. So when we talk about this, all right, this is a ratio of mass to volume. And this is a property like water. So the density of H2O liquid would be 1.00 grams per milliliter. Now technically that's at 4 degrees Celsius. That's where water is the most dense. And it gets less dense as you go hotter and less dense as you go colder. And then when it freezes, it's even less dense. So that's density. All right. So let's apply it real quick. A certain mineral has a mass, so it gives us a mass, which is wonderful. And that mass is 17.8 grams and a volume of 2.35 cubic centimeters. Question asks, what is the density? All right. So there's your question word, what? All right. Now, this problem is not what I would call breathtakingly difficult, but a good practice, because when things get harder, I'm going to say density. Density is the question mark, MV. Right? And we know D equals M over B. So mass, 17.8 grams. So I have that. And the volume is 2.35 centimeters cubed. And I have that. So I then can solve for the density. That's wonderful. Okay, so D equals, looks like we got 17.8 grams, and we have 2.35 centimeters cubed. So that means my density would be 7.57446809. That's what the calculator gives me. Oh, wow. Do we put all those numbers down? Well, the next topic we're going to talk about, we're going to do one more example, and then the next video, we're going to talk about how to do this. So the actual answer for this that I would want you to put down would be 7.57 grams per centimeter cubed. It has the number and the unit, right? So this would be the number and the unit. And those are both very important, all right? And I want to pick on the medical field a little bit because they've done this to you. I mean, your blood pressure, right? Oh, 120 over 60. Okay, what does that mean? What's 120? What's 60? All right, now it's actually millimeters of mercury. Your blood sugar level. Oh, your blood sugar is 100. That's good. 100 what? Well, it's 100 milligrams of glucose per deciliter of blood, right? And so they might do this. Oh, you go to the doctor. Ooh, yeah, your number's 7 and that's high. Oh, no idea if you don't have the unit. So you need the unit and then the number. And we're going to talk about how many numbers to keep. But as you can see, we have 3 numbers here and 3 numbers here, so 3 numbers there. All right, next one. We're going to do number 2 different ways. All right. First one, the same way we just did. We're going to read it. What is the mass? There's your question right there. You have a 49.6 milliliter sample, and it gives you a density of 0.85 grams per milliliter. So density is mass divided by volume. And I'm looking for the mass here, right? So I get mass by itself, multiply both sides by V. All right, so that means my mass would equal my volume times my density. And we can come over here, mass, volume, density. Mass is question mark, volume, 49.6 milliliters, and density is 0.85 grams per milliliter. So we put this in, M equals 49.6 milliliters times 0.85 grams per milliliter. So that means my mass would be 42.16, or we actually learned it's going to be 42 grams. And that's perfect. All right, that's a perfect way to do it. Now, what we are going to start to introduce, if you don't, you probably already know this, but we're going to start to introduce the fact that this is an amount, right? Your volume is an amount. It's an amount of something. It's something that we measure. And your density is a ratio, all right? Okay, so we're going to use the amount times the ratio, right? It's a great way to look at things. So if I take the amount, if I start with the amount, multiply that by the ratio, I'm going to get a good answer here, right? So if I take my 49.6 milliliters, and we're going to multiply that by our 0.85 grams per milliliter, right? If you notice, if we're doing a multiplication here, right, milliliters would cancel. And I'm left with the unit I want, grams, and I'm left with 42 grams. Okay? So both ways are correct. All right? And if you always do it the first way, I'm not going to be mad at you. We're going to do a lot of the second way, though, later on when we have amounts and ratios in chemistry. Because we take amounts, like how many grams of a certain substance, and then we know the ratio which it reacts. And so that is foreshadowing. Hopefully that makes sense. If there's any more questions, feel free to ask. Otherwise, we'll see you next time, guys. Take care.